What are the impacts of climate change on water resources on various aspects and how we can adapt to those changes? So let me briefly go through some potential impacts of climate change. First, what you can see is there are big shift in seasonal flow amount and flow timing. So this is a simulated results for the Willamette River Basin. The 2040s, which represent like a mid-21st century, and by the end of 21st century, around 2080s. But this is again combination of many different models. We call it ensemble mean. So we can see the general trend, what might happen in the future. So we know it's getting wetter, particularly toward the end of 21st century here, but summer is getting drier. But the thing is, the climate change impacts vary over space. So space does matter, the geography matters, and why? So this is an illustration showing why those two basins respond in a different way. And you can see those dark blue area, dark brown areas showing much further reduction in summer flow, like a 20 to 30% reduction in summer flow. But in those basins located in high cascade areas, did not show big reductions. And I took the two pictures on the same date. One basin located in the Western Cascade, which is laying on old geology, versus other basin in Clear Lake. You can see this basin, almost stream flow is very small, but stream is pretty replenished by groundwater. So the different geology explains those potential different responses to climate change. So you have to understand those background geology and natural characteristics. And also the previous speaker talked about the change in snowpack. I'm going to briefly skip through this. So this is again showing high cascade, how the snowpack may disappear by the end of 21st century under two different climate change scenarios. So A1B is a kind of mid-emission scenario. And B1 is low emission scenarios. So the mid-level emission scenarios, by the end of 21st century, so most high cascade basins, the snow will be gone. So we can also think about how those warming air temperature may increase water quality. So this is actually research done by University of Washington. I think it's part of the climate impacts group. So what they did is potential of future change in summer stream temperature starting from 1980s and 2020s, 2040s, and 2080s. So this is a background, a current maximum stream temperature ranging from 2 degrees to like 27 degrees. Not surprisingly, middle section of this Columbia River, you see a much high stream temperature. And how this stream temperature will change. And this is showing the shift in stream temperature. So not much change in the near future, but by the end of 21st century, up to like a 4 to 5 degrees Celsius warming. And particularly in those areas where we call it a transient. What that means is it's not rain dominated, but nor snow dominated. It's somewhere in between. So those located in the mid-elevation areas will experience more dramatic shift in stream temperature. You all know that what those changes mean in terms of salmonid species. But we also see some more frequent occurrence of those extreme hydrologic events, such as floods and droughts. And this is my co-author, and I studied this looking at the Willamette River Basin, how the frequency of 3 months drought may shift in the 21st century. Again, by the end of 21st century, under a high emission scenario, you get a more frequent occurrence of those extreme drought events. So particularly in the lower valley areas, which will have significant impacts on agriculture and other water-dependent industries. And finally, we can also think about the human consumption of water, how the climate change may increase those water demand. And this is using some empirical data, taking like a 500 households data in the Portland area. And you can consider from here to there, like under 20 degrees Celsius, we call it a base use. Essentially, it's a winter water use. But during summer times, people tend to use water more as temperature increases. So that's why the slope of that line is positive. So we expect as a temperature will get higher, people may consume more water. So that's the kind of implication of this graph. So this is what might be happening in the future. And but climate is only probably one of the other many stressors. We have to understand what other drivers may impact water resources. We all know that land cover change, particularly the urban development, will have significant impact in terms of timing and volume of flow. For example, as you remove those vegetation, what happens? So you actually lower deep infiltration. As a result, you get low base flow, like low groundwater flow, but you increase direct surface runoff. That urban runoff is a big problem in those big cities. So can you actually adapt to those changes? How can you create a surface that may be more porous? So when you think about the water resource management for sustainable future, we have to understand those three angles. The climate is one of the angles, but also we have to understand land use, land cover change, but how does the society respond to those changes? And then we have to know the various different aspects of water resources, not just single, because those are all related to some extent. So I would like to explain some potential adaptation strategies at like a different scales. We can look at like a whole watershed scale, but also more like a neighborhood, like a census block group scale, but at a more plot, a building or individual household level. So I'm going to explain about 3 case studies now. The first case study is looking at stream temperature in the Tualatin River. So Tualatin is a Native American language, by the way, meaning lazy. So the river is so flat, you can see a lot of the meandering section of the streams. So what we did is to actually subdivide the entire stretch of the river, about 154 segments. And we use a hydrodynamic model called the C-W2, which was developed by my colleagues at Portland State. And since this river is so flat, it violates a lot of water quality standards. It's been listed in 303 lists many times, and algal bloom is a frequent problem. So we try to model how we can actually improve stream temperature, but we have to understand what are the main driving forces of stream temperature change as they relate to climate change. So we know that stream temperature is a straight function of air temperature. So this slope line, which is close to 0.5, means that as you increase 1 degree Celsius of air temperature, stream temperature rise by 0.5 degree. But as you have more flow, you have to release more water. So the larger the water body, it takes more time for water to get heated. So stream temperature and water stream flow has an inverse relationship. But we know that climate change will shift those 2 variables. So the idea is, as we perturb the system, how the stream system responds to those changes. So this is the spatial temporal diagram. Remember that I mentioned about there are 154 segments. This is from upstream to downstream. And this is spatial extent, and this is looking at temporal extent. So starting from mid-May, like May 15, by the end of, and then ending mid-October. So we can look at the spatial and temporal pattern of stream temperature here. So not surprisingly, as you go further downstream, the stream gets warmer, but also in the middle of summer, it's warmer. But as you go toward early and later season, it's cooler. And we can also look at spatial extent. So this shows how many actually days streams temperature is exceeding 20 degrees Celsius. So 20 degrees Celsius is kind of a threshold temperature here. So for the upper part of the stream, less than like a fewer than 20 days, stream temperature exceeding 20 degrees Celsius. But toward the end of the mouth of the stream, it violates like over 60 days. And this is current, the base condition, like from 1990s and 2000. And this is under like a mid 21st century, which represents around the 2040s. And based on the ensemble mean, so the summer flow will be reduced by 5%, and air temperature will rise 1.5 degrees Celsius. So it's a combination of flow reduction and temperature increase scenario. And you can see how those red areas expand over space and time. So what that means is streams get warmer, and also those warm stream conditions stay longer. So that's the kind of implication. And those red areas also migrate further upstream. So that means a lot of sections of stream will violate the environmental standard. By the end of 21st century, much higher climate change scenario, like a 10% reduction in flow in combination with 3 degrees Celsius warming. So you can see those red areas further expand over space and time. But now, like, starting from July by the end of August, in the majority section of the stream temperature will be over like 22 degrees Celsius. So the question is, can you do anything? If this is going to happen, can you adapt to those changes? This is my son and his friend. So you can see a lot of the streams do not have big trees and vegetation. What if you plant trees? Can you actually lower stream temperature, and to what extent? So that's the question. So the Clean Water Service in Washington County, by the way, the Portland is here, the Columbia River, the Washington side is here. And they started some riparian enhancement project along those stream sections here. There's some tributaries. But the thing is, what we model is actually starting from here in the mid to lower section. There's no enhancement project at all. It's only located on those small tributaries and some further upstream. So this is an illustration of those examples. So instead of creating big wastewater treatment plant for the downstream, which will cost much more money, so they can redistribute those riparian areas in overall entire basin. But it will create some trails, so have some auxiliary benefits like recreation or aesthetics. We call it ecosystem services. That the ecosystem provide benefits to humans. So, and this is current condition. So you already saw this map, and this is no management. And what if you lower stream temperature by 2 degrees Celsius from those 6 tributaries, what impacts we'll see here? So there are some improvement near those junction of those tributary streams, but it's not going to affect much for the downstream here, the same message here. But what if you actually plant more trees, so you actually vegetate all the 10 tributary streams, and all the tributaries stream temperature will get lower by 2 degrees Celsius, we have more impact, but it's not good enough to affect further downstream. And the second case is also looking at the relationship between climate change and land cover and how water demand may shift in our Portland metro area. So this shows interesting geography of water consumption here. For those of you who are not from Portland, that's the Willamette River and that's Columbia. I exclude all the industrial land. That's why it's missing. It looks like a gun shape, but it's not actually. This all areas are important, but I exclude those industrial and some mountains. So those are census block group scale unit, and high water consumption areas are located in some suburban and upper neighborhood, like with high income and high educated people. And we relate that to this called temperature sensitivity, which means how much water consumption may increase in a given temperature increase. So the higher the number, that means in a given amount of temperature increase, people consume more water. So if you compare this map with the previous map, these two maps are highly correlated. Those high water consumption areas tend to have a high temperature sensitivity. So what this suggests is by changing a land use regulation or density, we could lower water consumption. So this could be used as a potential climate adaptation strategy. And the European Environmental Agency actually got this idea and they advertised in their newsletter here. So this is some simulated study. We look at some combined impacts of climate change and urban development, how when you combine those two, the impact could be much greater. But as you change a land regulation and as you develop a land more denser, you could actually lower some water consumption. That's the kind of message. And finally, at a more like an individual building or household level, we can also do something like this building. It was great actually to see building. Which maybe a LEED certified building, we can actually recycle water. Instead of spilling water to streams, actually we can retain water and release water gradually. And in Portland, we also installed those green streets. So you have green infrastructure. So those green streets can actually contain water during storm events and then release water gradually. So we don't actually have big flood events. But these kind of green streets also have some other benefits. When people see those streets, you see probably a feel, this is beautiful. So it has some kind of, you provide a peace or calm to you, and you can get some other benefits as well. So this is an example of the city of Portland is doing a Gray to Green program. So they have been implementing this program for like 5 years. And you can actually build this eco roof and lower air temperature as well as improve water, stormwater quality and create those riparian areas by purchasing some private lands. So instead of installing a big pipe, so which will cost a lot of more money, by redistributing those small infrastructure throughout the whole area, you can improve the environmental quality. So to conclude, so we know that the climate change will bring some additional stresses, but there is a hope. So by changing some land use regulation and creating more riparian buffers, we could adapt to those climate change. But also we know that it is a decentralized approach. Instead of one centralized approach like a big wastewater treatment plant or a big pipe, we install those small infrastructure throughout the entire area. They may be more desirable to adapt to climate change. But also, I suggest that we need to have some coordinated efforts between land use managers and water resource managers and at multiple scales. With that, so here's a polar bear. So what they say. But, so they can keep moving south. So its previous presenter mentioned that. So how do you plan for the future? So the future will not be like the same, but we can still learn lessons from the future, of the past. So thank you very much. Yeah.